Gilman is different than alkyl lithium and the Grignard because Gilman is less reactive. It's considered only as a nucleophile. So the R acts only as a nucleophile. It can never act as a base in there. The R can react with carbonyls that have leaving groups, specifically acid chlorides. Gilman has no reaction with a ketone. So this is the Gilman reagent. If I react Gilman with a ketone in there, because ketones are carbonyls with no leaving group, even though this R is a nucleophile. Okay, this R over here is a nucleophile, so you have two of them. You are just going to use one in the Gilman, just one of those and there. So this is going to act as a nucleophile, and that nucleophile is not very reactive. That nucleophile reacts if there is a leaving group. So the nucleophile here is going to do a reaction if there is a leaving group. If there's no leaving a group, then there will be no reaction in there. Even though this carbon is an electrophilic site, and even though this is a nucleophile in there, but because you don't have any leaving a group in here with the ketones, Gilman and ketones, they have no reaction. Gilmans can not react also with esters. So and this is the only example over there where we said that esters, they have ORs as a good leaving group. But in the solution where the Gilman is dissolved, ORs are considered to be not a good leaving group in there. So these are not good leaving group in the copper medium. So this is why Gilman and esters have no reaction. The only carbonyl, so Gilman doesn't react with ketones. It doesn't react with aldehydes, by the way. So ketone or an aldehyde. So it doesn't react with any carbonyl except the acid chloride. So Gilman reacts with acid chloride because chlorine is a good leaving group in there. So one of the R's of the Gilman, just one of the R's in there, the R is made up here of 3 carbons. So one of the R's from the lone pair is going to come attack the carbon of the carbonyl, form a negative charge on the oxygen, and you are going to end up having your addition in there to the carbonyl. So you are adding 3 carbons in there. These are the carbons of the carbonyl of the Gilman. You're going to form a negative charge on the oxygen there. Also, you have the chlorine. Chlorine is an excellent leaving group. So you can go ahead and do resonance and the chlorine is going to leave. So in this case, your product is going to be a ketone when Gilman attacks the acid chloride. So you're going to end up having a ketone in there. So all what you did is simply you replaced the chlorine with the R of the Gilman, whatever that R is, and your product is a ketone. Let's have another example. So here I'm having the CH3 as the R of the Gilman. Again, Gilman only reacts with acid chloride. So only reacts with acid chloride. This is the only carbonyl that Gilman reacts with. It doesn't react with esters, no ketones, no aldehydes in there. Gilman does not act as a base. So let's say, for example, if you have a carboxylic acid, it's not like the Grignard reagent in there, and you are using Gilman, CuLi, you're not going to have an acid-base reaction. So the CH3 here will not pick an acidic hydrogen. So there is no acid-base reaction. Gilman cannot attack the carbonyl, so it cannot do a carbonyl addition. It cannot do an acid-base addition, so there will be no reaction. The only carbonyl that Gilman attacks is the carbonyl that is connected to a halogen, because the halogens are good leaving a group for the Gilman medium. So the R is going to attack the carbon, form a negative charge, then it's going to close back, kick off the chlorine, and your product is always going to be a ketone. You have to know how to go backwards. So if you are given a ketone and you are asked to go ahead and make that ketone from a Gilman, always remember that these ketones, they come from acid chlorides in there. So pick whatever R side you want to be your acid chloride. So let's go ahead. If I want to go ahead and pick this R over here, you have to include the carbonyl with it. So you're going to go ahead and add a chlorine to this carbonyl to end up having your acid chloride in there. Then this CH3 will be one of the R's of the Gilman. We can also have another way of having our acid chloride. This is another route in there. So we can have our acid chloride to be the CH3 in this case. This means that our Gilman is going to be the ethyl in this case. So it's going to be two of those CuLi. Okay, so it's going to be two methods in there to make that ketone. As I said, whenever you are working with the R of the Gilman, you need to have a leaving group for the carbanion of the Gilman to attack. So it can attack an alkyl halide in this case. So the R, one of the R prime of the Gilman in there is gonna come, it's going to attack the R of the alkyl halide, and the halogen is gonna leave. Because those nucleophiles are not like regular nucleophiles in there. They are stronger than the regular nucleophiles that you know, the OH minus, the CN minus, etc. Those, they can attack any type of R. So the R in there is not limited to an sp3 hybrid carbon like the substitution SN2. No, the R over here can be an sp, an sp2, or an sp3. Any type of carbon in there. As long as you have a halogen, you will have a reaction. Let's have an example over here. So this is an alkyl halide. This is Gilman. So count your carbons. It's this carbon that is the carbanion. So it's this carbon that's going to form a bond between this carbon and this carbon over here. It's going to attack, kick up the bromine or kick off the bromine, and then you're going to end up adding it to your benzene. This is a good way to make a hydrocarbon, no matter what hydrocarbon that is. And I can continue these steps, these mechanism steps in there by introducing, for example, an oxidation step. Oxidation here is KMnO4. I can do KMnO4 and I can oxidize this carbon over here into a carboxylic acid. This is a benzylic carbon that can be oxidized into a carboxylic acid. I can use an sp hybridized carbon. As long as there is a leaving the group in there, the reaction can happen, and this nucleophile can come, attack the carbon, and the bromine is going to leave. You get your hydrocarbon. I can do an sp3 hybrid carbon in there, where this carbanion is going to come, attack this carbon, the bromine is going to leave. So notice here, I'm going to add to my carbon chain 2 additional carbons, 1, 2. So these are the 2 additional carbons in there. More examples over here. Now, if your alkyl halide is an sp2 hybrid carbon, then pay attention to the stereochemistry in there, because the stereochemistry needs to be the same. So this is going to be my alkyl halide, okay? And here my alkyl halide is a trans. So when the R is going to substitute that chlorine, it's going to be trans. It's not going to be cis. So the stereochemistry needs to be retained in this case. It's a straightforward. This nucleophile is going to come, attack the R of the carbon, and then the halogen is going to leave. But the attack here is going to keep the same stereochemistry where the halogen was. So the halogen was down in this case, and the stereochemistry around the double bond was trans. It needs to stay trans. So here I'm going to end up having my phenyl group in there, and then the CH3 stays in its place. So pay attention to that. If I start with the trans alkene and the alkyl halide, I need to end up having a trans product alkene as well. This is an example over here where my R is an sp2 hybridization. So here the R of the Gilman is an sp2. It really doesn't matter. I am going to add to this partial positive carbon. Bromine is going to leave. So I am going to end up simply adding to this carbon a double bond. This is what I'm doing. Count always your carbons so that you won't miss any carbon in there. The last reaction of the Gilman is the ring opening in basic medium. We said that Gilman is a nucleophile. So if Gilman is a nucleophile in there, and we have the epoxide, the O, to be a good leaving group, it can leave. So since I have a leaving group, I have my nucleophile in there, the reaction can happen. The attack is going to be on the less substituted carbon, opening up the bond. The oxygen is going to be negative, and then it's going to be protonated as before, and you're going to get your alcohol in this case. So let's have an example over here. I have my R of the Gilman. Just one of the R's is going to come, attack the less substituted carbon from the opposite side of the epoxide, open the epoxide up. Okay, with these reactions, normally also we use diethyl ether. So open it up in there, keep the same stereochemistry of the oxygen of the epoxide for the OH. So that is going to be a negative charge. The CH3 is at the back. You need to add your triple bond at the back in this case. So this is going to be my triple bond, and then in the next step, this is going to be step 2 of the reaction, and you are protonating in this case. The oxygen is going to come and take the hydrogen of the water or the acid. It really doesn't matter. You are going to end up having an OH in your product. The OH and the R of the Gilman needs to be trans with respect to each other in there. So this is your stereochemistry in here. So these two have to be trans with respect to each other. There are more problems in the problem set, so please practice them.